Drop a solid steel ball into the ocean, and it vanishes into the abyss in a matter of seconds. Yet, right now, across the world's most violent waters, machines made of 200,000 tons of that exact same steel are effortlessly gliding above the crushing depths. For centuries, the greatest minds believed that putting iron on water was a guaranteed death sentence. They were certain it would sink. They were wrong. But the secret to keeping these modern Leviathans from plunging to the seafloor isn't just about what they are built with. It is about what they are hiding inside. For thousands of years, the relationship between humanity and the ocean was governed by a single, undisputed rule of nature: ships were made of wood. Wood is naturally buoyant. A felled tree, left to its own devices, will rest upon the surface of a river. It was an intuitive truth. If you wanted to conquer the water, you used materials that belonged on the water. Steel and iron, on the other hand, belonged to the earth. They were heavy, dense, and unforgiving. Drop a piece of iron into the harbor, and it accelerates toward the bottom without a moment of hesitation. So, when the first engineers of the 19th century proposed building massive vessels entirely out of metal, the public and even seasoned mariners thought it was pure madness. It was not just seen as a dangerous experiment, it was considered an arrogant violation of the laws of physics. At the time, the skepticism was entirely justified. How could thousands of tons of metal, bolted together in a massive hull, do anything but drag its crew down to the dark seabed? The turning point arrived in 1843 with a machine that would forever change the scale of human ambition. Her name was the SS Great Britain. Designed by the visionary engineer Isambard Kingdom Brunel, she was a Leviathan for her era. Measuring over 320 feet long, she was the largest vessel ever constructed, and her massive hull was forged entirely from iron. When the time came for her launch, crowds gathered with a morbid curiosity, fully expecting the great iron beast to plunge straight into the mud of the Bristol Channel. Instead, as the moorings were released and the colossal weight hit the water, something extraordinary happened. The iron did not sink. It sat high and proud on the surface, effortlessly defying the gravity that should have doomed it. This moment shattered centuries of maritime intuition. But it was not magic. Brunel and the pioneering engineers of the industrial age were not defeating the laws of nature, they were exploiting a hidden loophole in them. They understood that the buoyancy of an object is not determined merely by the material it is made of, but by the space it commands. They had built a shell of heavy metal, but the vast majority of the ship's internal volume was simply empty air. As long as the total weight of the iron and the air inside was less than the weight of the water it pushed out of the way, the ocean had no choice but to push back. The vessel was cradled by an invisible, upward force. The iron illusion was broken. Humanity realized that if they could trap enough air inside a metal shell, there was theoretically no limit to how heavy a ship could be. The era of wooden vessels was over, and the age of the metallic giants had begun. Yet, keeping an iron ship afloat in the calm, controlled waters of a dockyard was only the very first step. Out in the open ocean, where the water is never still and storms can rip steel structures apart, a new and terrifying problem emerged. A floating metal box is completely useless if the ocean can easily tear it open and replace the buoyant air with crushing water. To understand how a modern megaship survives, you have to look at it not as a vehicle, but as a perpetual battleground. Every second a ship is in the water, it is locked in a violent, invisible war between two fundamental forces, the relentless downward pull of gravity and the desperate upward push of the ocean. If gravity wins for even a single moment, the ship becomes a submarine. The secret to winning this war lies inside the vessel. If you were to slice a modern 200,000-ton cargo ship in half, you would not see a solid block of metal. You would see a cavernous, cathedral-like emptiness. Over 2,000 years ago, a Greek mathematician named Archimedes discovered the rule that governs every vessel on Earth today, the principle of displacement. When an object is placed in water, it must push a certain amount of that water out of the way to make room for itself. But the ocean is heavy, and it desperately wants to rush back in and fill that space. As it tries to reclaim its territory, the water pushes back against the hull. The physics are beautifully simple, yet entirely counterintuitive. As long as the ship weighs less than the exact volume of water it just pushed away, the ocean will hold it out. Imagine a solid cube of steel measuring 10 by 10 feet. It weighs roughly 280 tons. Drop it into the ocean, and it sinks instantly. The small amount of water it displaces cannot possibly push back with 280 tons of upward force. But if you take that exact same amount of steel, melt it down, and forge it into a massive, hollow box the size of a football field, the total weight of the metal has not changed by a single ounce. However, the volume of water this new shape pushes out of the way is now exponentially larger. The upward push of the sea becomes vastly greater than the downward pull of the steel. The geometry of emptiness turns a sinking weight into a floating fortress. A modern Megamax cargo ship displaces around 250,000 tons of water. That is the equivalent of physically moving a small mountain of liquid out of the way just to exist on the surface. And the ocean pushes back against the hull with that exact same force. But an empty ship is just a massive steel balloon. The sole purpose of a commercial vessel is to carry cargo. Thousands upon thousands of tons of it. As giant cranes load containers into the massive hollow bays, the ship becomes heavier. Gravity begins to pull harder. To compensate and generate more upward force, the ship must push more water out of the way. This means the colossal steel hull sinks deeper and deeper into the crushing depths. The deeper it goes, the higher the hydrostatic pressure climbs on the outside of the hull. With the ocean constantly probing for a weakness, waiting for a chance to rush in and replace the buoyant air with heavy water. There is a mathematical limit to this game of tug-of-war. If the ship sinks too deep, the water will overtop the deck. The cavernous emptiness will fill, the density will instantly change, and the ship will plummet. To prevent this, maritime engineers paid a simple, unassumingly small mark on the side of every commercial ship in the world, the Plimsoll line. It is a visual boundary, the absolute physical limit of displacement. Cross this line, and you invite catastrophe. But managing the weight is only half the battle. Because when you stack 20,000 steel containers into a towering skyscraper above the deck, you are not just pushing the ship deeper into the water. You are fundamentally altering its center of gravity. And out in the open ocean, a top-heavy ship does not just sink. It rolls. Keeping a massive steel structure on the surface is a matter of volume. But keeping it upright is a matter of geometry. And gravity is a relentless opponent. If it cannot pull a ship straight down, it will try to roll it over. When you look at a modern Megamax vessel fully loaded in port, the sight defies logic. Above the deck, cranes stack up to 20,000 steel containers, creating a massive, blocky skyscraper towering 10 stories into the air. The sheer mass of this cargo raises the ship's center of gravity higher and higher above the waterline. Imagine trying to balance a heavy steel hammer on the tip of its handle while standing on a moving floor. That is the exact physics problem a fully loaded cargo ship faces. Every wave, every gust of wind, and every turn of the rudder threatens to tip that towering weight past the point of no return. Once the center of gravity shifts beyond the upward support of the displaced water, the ship will inevitably capsize. To prevent this disaster, engineers do something that sounds completely insane. They use the ocean itself as a counterweight. Hidden deep in the bowels of the ship, wrapped around the cargo holds and nestled inside the double hull, is a vast network of empty chambers. These are the ballast tanks. As the towering stacks of containers make the ship dangerously top-heavy, high-powered pumps flood these lower tanks with thousands of tons of raw seawater. It seems like a fatal contradiction. The entire principle of buoyancy relies on keeping the heavy ocean out, yet maritime engineers deliberately pump it inside. But this captive water serves a critical purpose. It acts as an invisible anchor, dragging the vessel's center of gravity plummeting back down beneath the waves. This creates a dynamic equilibrium. The ship becomes a colossal pendulum. When a massive wave strikes the side of the hull, the ship rolls. It actually has to. If the steel were completely rigid and resisted the wave entirely, the blunt force of the ocean would eventually shatter the hull. The roll absorbs the kinetic energy of the sea. But because of the thousands of tons of heavy ballast water trapped in its belly, gravity acts like a coiled spring, yanking the massive ship back upright. It is a terrifyingly delicate balancing act. If the crew pumps in too much ballast, the ship becomes what mariners call stiff. It sits too heavily in the water. And when a wave hits, it snaps back to vertical so violently that the whiplash can snap steel cables, sending hundreds of containers cascading into the sea. If there is too little ballast, the ship becomes tender. It rolls lazily, taking far too long to recover. In a severe storm, a tender ship might roll over just far enough that it never comes back. By mastering this balance, modern Leviathans can survive the brutal, rolling chaos of a violent storm. They can tilt to alarming angles and fight their way back to the sky. But the ocean is a three-dimensional battlefield. While the ballast tanks solve the problem of tipping side to side, they offer absolutely no protection against an entirely different threat. Out in the deep ocean, waves do not just hit the sides of a ship. They pass directly underneath it. And when a vessel is longer than 3 football fields, a single wave can turn the ship's own massive weight into a weapon, one capable of tearing its steel spine in half. To comprehend the sheer terrifying scale of the ocean's power, you have to picture the dimensions of a modern megaship. The largest cargo vessels today stretch over 400 meters long. That is longer than the Eiffel Tower laid flat on its side. On land, a structure of this immense size rests upon a solid, immovable foundation. But at sea, the foundation is liquid, chaotic, and constantly changing shape. When a ship of this length sails into a major storm, it encounters ocean swells that can be hundreds of meters wide. Imagine the ship riding to the exact crest of one of these massive waves. For a few agonizing seconds, the center of the hull is pushed upward by the water, while the bow and the stern are left hanging over deep, empty troughs. This creates a lethal structural condition known in naval architecture as hogging. Gravity violently pulls the unsupported ends of the ship downward. The steel on the bottom of the hull is compressed, while the steel on the upper deck is stretched to the breaking point. threatening to snap the great vessel in half over the peak of the wave. Seconds later, the wave rolls forward, and the situation violently reverses. Now, the bow and the stern are supported by two separate wave crests, while the massive, heavily loaded center of the ship hangs unsupported over a deep trough. This is called sagging. The immense weight of the cargo pushes the middle of the vessel down, reversing the stress forces entirely. If a 400-meter hull were made of perfectly rigid, unyielding iron, these alternating forces of hogging and sagging would fatigue the metal and shatter it like a dry twig. The secret to surviving this relentless assault is not extreme rigidity, but calculated flexibility. The entire hull is designed to bend. If you were to stand inside a long corridor deep within the bowels of one of these leviathans during a heavy storm, you would not just feel the movement. You would see the long steel hallways visibly warping and bending around you. You would hear the deafening, unearthly screech of thousands of tons of high-tensile steel stretching and contracting. Engineers reinforced the hull with massive longitudinal girders, essentially creating a mechanical spine. This allows the ship to undulate, absorbing the kinetic energy of the waves by flexing like a giant metallic serpent. The steel is mathematically engineered to endure millions of these bending cycles over its lifespan. As long as the waves arrive in a predictable, rhythmic pattern, the flexing hull can absorb the punishment. But the deep ocean is rarely predictable. And out in the darkest, most violent stretches of the sea, waves do not always follow a rhythm. Sometimes, the ocean generates a geometric nightmare, a chaotic convergence of energy that pushes even the most flexible steel past the point of no return. For decades, mariners returned to port with terrifying stories of walls of water appearing out of nowhere. These accounts were largely dismissed by scientists as hallucinations or nautical myths. Standard mathematical models of the ocean simply did not allow for waves of that size. But in the late 20th century, oceanographers were forced to admit a terrifying truth: road waves are entirely real. And for a modern megaship, they are the ultimate test of survival. A road wave is not just a large ocean swell. It is a mathematical anomaly. A sudden, near-vertical wall of water that can reach towering heights of 30 meters, roughly the size of a 10-story building. When a megaship encounters a wave of this magnitude, the physics of buoyancy are pushed to their absolute breaking point. As the bow crashes into the sheer face of the wave, thousands of tons of solid green water slam onto the forward deck. For a heart-stopping moment, the ship stops displacing water and is instead buried beneath it. The cavernous, buoyant air inside the hull is useless if the sheer weight of the ocean from above crushes the steel inwards. The entire vessel shudders, the engines scream against the sudden resistance, and the ship must violently force its way back to the surface. Yet, a single massive wave is not the only monster hiding in the deep. Sometimes, the most lethal threat comes from a rhythm rather than a random strike. When a ship sails into a sea where the distance between the wave crests perfectly matches the length of the ship itself, a devastating phenomenon known as parametric rolling can take hold. It starts subtly. The ship rolls just a few degrees. But as the bow pitches down into the next trough, the geometry of the hull interacting with the water rapidly changes. The vessel suddenly loses a fraction of its stability. As it rises again, it snaps back. If the timing of the ocean waves perfectly matches the natural rolling frequency of the ship, the sea acts exactly like someone pushing a child on a swing. Every single wave adds more kinetic energy. Within a matter of minutes, A gentle 5-degree sway violently escalates to 10, then 20, then an agonizing 30 degrees. The forces acting on the cargo above deck become catastrophic. At 35 degrees, the massive steel lashings holding the container stacks together begin to snap like dry thread under the extreme centrifugal force. Entire rows of containers, weighing thousands of tons, are violently hurled into the Black Ocean. To break this deadly resonant cycle, the captain must instantly change the speed and direction of a 200,000-ton behemoth. But altering the momentum of an object that massive takes time that the crew simply does not have. It is a terrifying realization. Despite the ingenious application of Archimedes' displacement, carefully calculated ballast tanks, and flexible steel spines, the ship remains at the absolute mercy of the ocean's chaotic energy. And as international trade demands that these vessels grow larger with every passing decade, maritime architects are rapidly approaching a hard, physical boundary. There is a limit to how big a steel ship can actually get before the ocean refuses to let it float. The arms race of maritime engineering has not slowed down. In fact, it is accelerating. Today, a new class of ultra-large container vessels has shattered the 24,000 TEU barrier. Ships like the MSC Irina are no longer just vehicles, they are floating industrial islands, stretching nearly a quarter of a mile long. But as these dimensions continue to expand, the margin for error is rapidly shrinking. We are approaching a terrifying intersection. As naval architects push the absolute physical limits of steel and buoyancy, the environment these Leviathans sail into is fundamentally changing. Warming global temperatures are injecting unprecedented levels of thermal energy into the world's oceans. The result is a new era of maritime weather. Cyclones are intensifying faster. Storm systems are growing larger, and the terrifying rogue waves that were once considered rare. Generational anomalies are being recorded with alarming frequency. This changing ocean traps modern engineers in an impossible paradox. To survive these increasingly violent superstorms, a ship's hull must be incredibly strong. But if the steel plates are forged too thick, the vessel becomes too heavy to carry a profitable amount of cargo, defeating its entire purpose. Conversely, if the steel is too rigid, it loses its vital ability to flex. Without that flexibility, the massive hull cannot absorb the kinetic energy of the sea, and it will eventually snap under the extreme hogging and sagging forces of a monster wave. There is a hard, mathematical ceiling to how much stress high-tensile steel can take before its molecular bonds simply tear apart. And as the storms grow stronger, the ships are getting closer and closer to that invisible boundary. We are no longer just fighting the downward pull of gravity, we are testing the ultimate endurance of the materials we pull from the Earth. The engineers of the 19th century proved that humanity could conquer the seas not by fighting the water, but by displacing it. They trapped air in iron cages and built a global civilization on the backs of metal giants. But as we continue to stretch these floating fortresses to their absolute limits, a chilling question remains hovering over the dark waters of the deep ocean. Today, standing on the observation deck of a modern 24,000 TEU container ship as it cuts through the black expanse of the open ocean, the illusion of permanence is absolute. It feels impossible that this mountain of steel is essentially floating on trapped air, suspended precariously over thousands of meters of crushing abyss. The triumph of the modern megaship is not that we conquered the sea. It is that we learned to speak its language. By mastering Archimedes' ancient principle of displacement, balancing towering weights with thousands of tons of hidden ballast, and engineering steel spines that flex and breathe with the rhythm of monster waves. Humanity built a global civilization on the backs of metal leviathans. Yet, as these floating islands grow ever larger, and as a warming planet unleashes increasingly violent weather systems upon the world's shipping lanes, we are hurtling toward a silent reckoning. We have pushed high-tensile steel to the edge of its molecular endurance. The laws of physics are patient, but they are absolute. The ocean does not yield its supremacy, it merely waits to see how much weight we dare to trust to the air. Which engineering marvel or deep water mysteries should we explore next? If you enjoy journeys into the hidden mechanics of our world, subscribe for the next documentary.